Assalamualaikum. We are from Team 5. We'll be presenting our group project about solar wind hybrid generation system.
Our project presents the design of a hybrid renewable power generation system that combines solar thermal energy and wind energy. By integrating two sustainable sources, the system aims to provide a stable and continuous supply of electricity. The solar thermal system captures and converts sunlight into heat that will be used to generate steam for power production. In parallel, the wind system captures kinetic energy from wind to produce electricity. Together, these sources complement each other. Solar energy provides power during the day while the wind during the night. This hybrid approach enhances the efficiency and sustainability of renewable power generation, supporting a cleaner and more stable energy future. So how our power generation system works? Our power generation uses solar thermal and wind energy to generate electricity. For solar, sunlight will heat a fluid in the solar receiver. This hot fluid goes to boiler to create steam which spin the turbine. After producing electricity, the steam is cooled, pumped back and the cycle repeats. For the wind part, wind will turn on the blade of a rotor. This movement then goes to a generator that produces electricity. Both energy sources send their electricity through a step-up transformer. Then it goes to a substation and finally to a power grid for distribution.
For overview of process flow, this project presents a hybrid energy generation model that combines renewable energy sources with a conventional Rankine vapor cycle. The model features several key components that work together to efficiently produce electricity. The renewable sources in the system include a solar panel and a wind turbine. The solar panel is used to provide thermal energy, which may assist in preheating the working fluid, while the wind turbine directly contributes 22 megawatts of mechanical power, which is converted into electricity through a generator. The core of the system is the Rankine cycle, which consists of a boiler, turbine, condenser, and pump. The boiler heats water to a high pressure of 15 MPa and a temperature of 400 degrees Celsius, generating superheated steam. This steam then enters the turbine where it expands and performs mechanical works, producing 100 megawatts of power. After passing through the turbine, the steam enters the condenser where it is cooled down and converted back into liquid water. The condenser operates at a low pressure of 10 kPa and a temperature of 45.81 degrees Celsius, which help efficiently condense the steam. The condensed water is then pressurized by a pump and sent back to the boiler, completing the cycle. Finally, the electricity generated from both the wind turbine and the vapor cycle is passed through a transformer and collector substation. This prepares the electricity for delivery to the power grid, ensuring it meets voltage requirement for transmission. Overall, the purpose of this model is to demonstrate how renewable sources like wind and solar can be effectively integrated with traditional thermodynamic cycles to create a more sustainable and reliable power generation system.
Now we will proceed to the solar thermal efficiency calculation. Solar power efficiency refers to the efficiency of converting solar energy into heat, which is the thermal efficiency. So first of all, we will take a look at the process flow diagram. So the first stream is the stream 3, which the stream that go into the turbine. The phase of this stream is at a superheated vapor and have a pressure of 15 MPa and a temperature of 400 degrees Celsius, which this information we get from our reference. Now, by knowing this information, we can get the H3 and S3 from the table of superheated vapor. Next, we will proceed to the stream 4, which the phase is at a saturated liquid and have a pressure and temperature of 10 kPa and 45.81 degrees Celsius. So, we know at the stream 4, the S4 is equal to the S3, which is 5.8819 kJ over kgK. And with this all information, we can get the H4. Next, we will proceed to the stream 1, which have a phase of saturated liquid and a pressure and temperature of 10 kPa and 45.81 degrees Celsius. So from this information, we also can get the H1 and V1. But for the S1, it is equal to the S2. So next, we will go to the stream 2, which have the phase of compressed liquid and have a pressure and temperature of 15 MPa and 12 degrees Celsius. Which with this information, we can get the H3 is 118.64 kJ and the S2 is 0.3614 kJ over kgK. Now we will move to the calculation to find the quality, which is dx. So we will use the stream 4 and the equation of S4 is equal to SF plus X times with SFG. So for the value we already have, which is S4 is equal to 5.8819, and for the SF 0.6492, and lastly for SFG we have 7.4996. And by doing the calculation, we get the quality is equal to 6.898. So we will move to the stream 2 to find the S2 and H2. So by doing the interpolation, we can get the value, which is H2 is equal to 118.64 kJ over kg, and for the S2 is 0.3614 kJ over kg K. And by having all of this information, we can proceed for the calculation of work in, which the equation is V1 times with P2 minus P1. So the value of V1 is 0.001010, and for the P2 is 15,000, and lastly for P1 is 10. So by calculating this, we get the work in is 15 kPa. Now we will move to the calculation of efficiency, which the equation is 1 minus QL over Q hash. So we can change the equation by substituting the QL and Q hash, which is QL is equal to H4 minus H1, and for the Q hash is H3 minus H2. So we can get all this value from the process flow diagram, which is H4 is equal to 1861.496, and for H1 is 191.81, and for H3 is 2975.7, and lastly for H2 is 118.64. And the value of efficiency we get is 0.416. Now we move to the calculation of workout, which we use the equation of H3 minus H1, and the value of H3 is 2975.7, and for the H1 is 1861.496, and the value of workout is 1114.204 kPa. And lastly, we will calculate the work net out, which the equation is work net out is equal to work out times with mass flow rate. So work net out we already have, and the work out we already have. Now we will find the mass flow rate. So we will change the equation by having the mass flow rate is equal to work net out divided by work out. So the work net out is 100,000, and for the work out is 1114.204, and the value of mass flow rate we get is 89.75 kg over second.
Wind power efficiency means converting the wind's kinetic energy into electrical energy. To calculate the power from the wind turbine, we use this formula, where air density equals 1.225 kg per meter cube. A is the swept area from the plates. Wind speed equals 12 meters per second. The power coefficient equals 0.593. First, we calculate the area. Area equals 43700 meters square. Now we substitute the value into the equations. The result is 22 megawatts. So the wind turbine can generate up to 22 megawatts of electricity when the wind speed is 12 meters per second.
Let's look at a quick comparison of four power generation system: the solar wind hybrid, wind only, the GMA is coal-fired power plant, and solar PV system. The solar wind hybrid system uses both solar thermal and wind energy, while the system runs purely on wind. The GMA is plant relies on coal, and the solar PV system uses sunlight. In terms of efficiency, the hybrid system has a thermal efficiency of 41.6%, slightly better than the 40% from the coal. Wind has a higher electrical efficiency at 53.9%, while solar PV system range from about 16.7% to 22.8%, depending on condition. Looking at power capacity, the hybrid system generates 122 megawatts combined from solar and wind, whereas GMA is produce a massive 2000 megawatts. Solar PV system are much smaller in comparison, usually under 1 kilowatt per panel.
As for the process, both the hybrid and coal system use the Rankine cycle, while wind converts mechanical energy directly into electricity. Solar PV system use direct electrical conversion from sunlight. Each system also differs in equipment and fuel. Solar use collectors and heat transfer system, wind use rotors and generators, and coal requires boilers and emission control equipment. The hybrid system can also include battery storage, while the coal plant may use biomass co-firing to reduce emissions. Finally, in terms of environmental impact, renewable systems like the hybrid, wind, and solar have no emission during operation and very low carbon footprints. In contrast, coal emits CO2, SO2, NO, and other pollutants, making it far less environmentally friendly.